Okay, Ka of acetic acid. Go down to discussion questions. Did y'all understand how the titration curve gives you the information you want? We need to talk about that maybe. Let's see, is that one of the discussion questions? If it's embedded in the discussion questions, I'll just move on. Here we go. Define terms. No. No, it doesn't. So let's do that first. You're gonna titrate a point, I think 25 milliliters of a 0.1 molar um, acetic acid solution. You can have 0.1 molar acetic acid solution. And you're going to titrate that with 0.1 molar sodium hydroxide solution. Okay. And what you're going to end up with is a series of data. Right? You're going to have volume of acid. No, you're not going to have that. You're going to have the x-axis is the volume of base, right? The volume here versus pH. Okay, so you're going to have a series of data points here based upon how they tell you to do it. I think they go through. You start off with fairly large aliquots amounts of base, and then when you get close to the inflection point, it slows down like to maybe 1 or half a mil until you get past that, and then you speed it up again. Okay, how does that plot out? The volume of base is controlled by U. That means it's x-axis. This will be in milliliters. And this is the pH. Okay, we're going to start out at something like, I don't know, 4.3 maybe, or 3.8. It varies. So we're in the neighborhood of between 3 and 4. Starts out, right, increasing the pH as you add base. But once you've, let me do the governing equation, right, the titration equation. So you've got HC2H3O2 aqueous plus sodium hydroxide. Aqueous is in equilibrium with water plus sodium acetate, C2. So what you got here is a situation where, and this aqueous solution is dissociated. These are separate ions. But this is not separate. And these are separate. So as you add base, you're building up some conjugate base of the acid, right? And as you get more of this strong conjugate base, right? If this is a weak acid, that's a strong conjugate base. Now it's able to buffer the system. In other words, if you put more base in there, it's going to react with this. If you pour any acid in there, it's going to react with that. So in that region, it will flatten out. And this is the buffer zone right here. And then once you've exhausted this, most of this, then it starts to climb because you're adding base and the base is not being consumed. And it goes steep like that. And then once you reach a certain point where you got so much base that addition of a little bit more doesn't make a difference in the pH. This point right here, in the middle of that steep part, is the equivalence point. Okay. And it will correlate to a given volume. Okay. Now, remember from Henderson-Hasselbalch equation, if you want to know the pH of the solution, you need to know the pKa of the weak acid, yeah, plus log of the conjugate base. In our case, the conjugate base is C2H3O2 minus divided by the acid, C2H3O2. Okay. There you go. That's Henderson-Hasselbalch. So at any point on this curve, this formula works. Anywhere in here, the pH is based upon what the pKa of that acid is and the ratio of these two. Right? Now, under what conditions would pH equal pKa? When this amount is equal to that amount. If they're equal, then this term is 1, and log of 1 is 0. It's 10 to the 0 power equals 1. So that whole thing then drops to 0. And at that point, pH equals pKa. So when does that happen? Well, the amount of acid is equal to the amount of base right here. So we've consumed all of the base, all of the acid when we get to this point. At what point then would only half of this be consumed? Because that's where you get this is equal to this. If only half of this is consumed, then half of that goes over here, and now they're equal in concentration. If you only use up half of this in the titration, now you've got equal amounts of conjugate base and acid. That happens right here. Right here. At 1/2 equivalent. So if it takes, I don't know, just for argument's sake, if it takes 20 milliliters, well, let's say 30 milliliters. If it takes 30 milliliters of base to neutralize, to reach this equivalence point, where would you look on your graph to find half of that? At 15 milliliters. And then you would follow it up here. And that over here, right there, is your pKa. Okay. Now, how do you find the Ka from that? Go back to your definition. pKa is equal to the negative log of the Ka. So you just move the negative over here and make that the power of 10. So it's 10 to the negative pKa equals Ka. The sources of error here are not just plotting the data, but reading the graph. So once you've plotted your data, the better you can plot it, the larger format will give you less error. So use the entire page. And then this is a calculation. You know, here is easy to find out where this value is. And then half of that gives you the pH at half equivalence. But once you read that, if this is drawn correctly, then you can read that and find the pKa pretty close, but there will be some, some experimental error introduced there. Okay. That's the whole point of this exercise, is to be able to plot that information. And if you don't plot that in your report, then it's incomplete. Right? You put all your data in there in your table, but then you do have to plot the graph and draw your best fit curve, because your values might wiggle a little bit. You want the best, smoothest curve you can fit in those data points. Then you can read your graph. Because this half point might not have a value over here. if this takes 30 mils and you actually have a titration point where you added 15 mils, then you can go straight to your data table and find the point on your graph. So at what pH did that occur, right? Then you can do that without having to go to graph. But if this half equivalence point is not in your data set, but it's an interpolation, then you have to go to the graph and read across. Okay. All right. So that's the experiment in a nutshell. A big nut. I'll leave that there in case we need it. All right, let's go to the discussion questions. All right, let's see. We'll go down, 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 down. Here we go. Discussion questions. Number 1. A. These are definitions. Define these terms. Equivalence point. I just told you what it was. The equivalence point is the point at which acid equals base. The amount of acid you have in there equals the amount of base. Now, this can be, if this is a one-to-one relationship, you're fine. You can say moles of. But if you're titrating a diatomic or a triatomic or a polyatomic acid with a monohydroxyl base, then you have to say, rather than moles of acid, moles of base, you have to say moles of hydrogen ions equals moles of hydroxyl ions. That will work for any combination of acids and bases. Okay. B, endpoint. Endpoint is not a problem for us in this class, but it was for first semester. We were determining the molar mass of citric acid. We used an indicator. The endpoint is equal to color change for the indicator. And you pick your indicator so that it will change colors near the equivalence point. I don't think I've ever seen one hit it exactly. But the slope is so steep here that if you get close to it, then that's good enough for calculations. All right, what's C? Ka. This is the acid ionization. Some people say dissociation. Ionization constant. Right. And the pKa, you can simply say the pKa equals the negative log of Ka. Okay. That was number 1. Number 2. If 23.9 milliliters of sodium hydroxide solution is required, let's see, sodium hydroxide, 23.9 milliliters, sodium hydroxide is required to titrate 25 milliliters of acetic acid, C2H3O2. And this is to the equivalence point. We have, what, 25 mils? Yeah, 25 mils. Is that 23.9? Just 23.9 milliliter. But we know the concentration of the acetic acid is 0.105 molar. Right? What is the concentration of sodium hydroxide? Again, if your base is monohydroxyl and your acid is monoprotic, then this equation will work. how do we define molarity? Molarity is moles per unit volume, right? So if we rearrange that to moles times volume equals number of moles, then we say the number of moles of acid equals the moles of base. So how do we calculate moles of acid? Well, the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. We want to know the molarity of the base. So we solve for the molarity of the base. That's molarity of acid, volume of acid, divided by volume of base. Molarity of the acid is 0.105, and the volume is 25 milliliters, divided by the volume of the base, which is 23.9 milliliters. That will give us the molarity of the base. Right? Just algebra. This is 0.110, rounded off, molar. Rounded to 3 places. Again, if we have, say, a diprotic acid and a monoprotic base, then the stoichiometry changes, and we can't use this formula anymore. In its place, we have to calculate the normality. I think we talked about that last semester. No, this semester. Normality? Yeah. You have to use normality then. Or you use the balanced equation and work from there. 2. 3. Number 3, discussion question. Number 3. In the titration of a weak acid, the midpoint of the buffer zone corresponds to a pH of 6.1. The midpoint of the buffer zone, that's this flat point right here. The midpoint is 6.1 pH. Okay, that's equal to the pKa of that acid. What's the pKa and the Ka? Well, we found it. pKa equals 6.1. The Ka equals 10 to the minus 6.1. Because this is equal to negative log of the Ka. So we move the negative over here, then that becomes the power of base 10. 10 to the minus 6.1. 6.1, change the sign and do 10 to the x. This is 7 point, let's see. Same thing for pH and pKa. The number of decimal points, let's see, the number of significant figures in the concentration equals the number of decimal points. So it's only got one significant figure. All right, we have to say 8 times 10 to the minus 7. Because we only have one decimal point, one significant figure. Okay? And that's definitely weak acid. 10 to the minus 7. Yeah, because this is a formal report. Yeah. Yeah. If you don't have room on one side, that's what the left-hand side is for. Just be sure that you. Oh, I see what you mean. Yeah, you can do that. Let's see, that was discussion. Then we can go to pre-lab questions. All right. One, write the balanced molecular equation for the titration of acetic acid and sodium hydroxide. Here's the acid, C2H3O2 in aqueous solution. We're titrating with sodium hydroxide, this, and what are our products? All acid-base reactions. You get water as one of the products, and you get the salt, sodium acetate. That's the complete molecular equation, and it's balanced because there's only one of each. Right? One hydrogen and one hydroxyl makes one water, and then sodium with acetate. We're good. That's the balanced molecular equation. Okay. 2. Let's see, that was 1. There we go. Let's do 2. Two says the Ka of formic acid is 1.8 times 10 to the minus 4. So the Ka of formic acid equals 1.8 times 10 to the minus 4. 8, 10 minus 4. And the Ka of lactic acid is 1.4 times 10. I'm going to put that one down here. This one's the lactic acid. Everybody knows. You've been sedentary for a while and you go back to exercise, you'll know what lactic acid is. It builds up in your muscles and makes them sore. 1.4 times 10 to the minus 4. There we go. All right. Question. Which acid is stronger? The stronger acid is the one with a smaller Ka. So they both have the same power of 10, so we look at the coefficient. This is a bigger number. So this is stronger. Formic acid is stronger than lactic acid in a chemical sense. And then the pKa's are simply negative log of 1.8 times 10 to the minus 4, negative log of 1.4. Take the log and change the sign. 3.74. Yeah, two significant figures. 3.74. We can have two decimals. And then 1.4 exponents. 4. And take the log of that, change the sign. 3.86. 3.86. All right. So since this is a negative log function, you can also look at the pKa's. This is the pKa of formic acid, and this is the pKa of lactic acid. We can compare the pKa's, and since it's the log is inverted by this negative sign, then the smaller pKa is the stronger acid. So the larger Ka or the smaller pKa determines the strength of the acid relative to any of the others. Oh, that's it. That's all the discussion in pre-lab questions. Just those two. Yes. They're not necessarily strong acids, but they're stronger than others. This is a comparison. Let's see. A Kb, yeah. A Kb for a base, the larger the Kb, the stronger the base. So if you had a pKb, the smaller the pKb would be the stronger base. Yeah, that's true.